This is the final equivalent circuit assuming large capacitors, and this basic amplifier, this is known as a common source amplifier because the MOS transistor has gate, source and drain, and the input is applied to these 2 points. This Vs somehow appears between these two, or a fraction of it will appear. So, the input is applied to gate source and the output is taken between the drain and source terminals. Okay. So, given these, the source terminal is common to the input and output, that is why it is called a common source amplifier, and this is the very basic type of amplifier you can build with a MOS transistor. Okay. Now, let us analyze this, it is quite easy. That is the common source amplifier, and what do we have here? We have Vs, Rs, and this whole thing can be replaced by a single resistor, which is R1 parallel R2. Okay. And you can see that these two resistors form a voltage divider driven by the source Vs. So, this voltage here, which is VGS, this is equal to Vs R1 parallel R2 by R1 parallel R2 plus Rs. Okay. Quite easy, and this is approximately equal to Vs if R1 parallel R2 is much more than Rs. And for this condition to be satisfied, you know that both R1 and R2 have to be much more than Rs. Okay. So, this component here, remember this R1 and R2, these are there for biasing the transistor, biasing the gate of the transistor, and they do have some effect on the circuit. Okay. The actual gate source voltage applied is smaller than the input voltage Vs, but you can fix the situation by making R1 and R2 very large, and fortunately you can do that because this R1 and R2 forms a voltage divider for this supply, and it supplies the gate of the transistor. Now, if the gate draws some current, okay, that will change the voltage here. Remember, the open circuit voltage here, because of the voltage divider, is VDD times R2 by R1 plus R2. But if some current is drawn from it, okay, the voltage will be different. So, you can analyze this circuit for yourself and then see. Please use superposition to analyze this and convince yourself that this is the case. You know the open circuit voltage here, that is VDD times R2 by R1 plus R2. Okay. Now, imagine that there is some current I gate, the gate current was being drawn from it. What will be this voltage? You please calculate that and see for yourself that it changes. But in our case, Ig is 0, okay, no current is drawn. So, this voltage will not change at all regardless of the value of R1 and R2. You will see that if there is a gate current, then you can't make R1 and R2 arbitrarily large, but now you can. Okay. So, that way, although these two resistors R1 and R2 have some effect on the circuit, you can ignore that effect by making R1 and R2 very large, and there is no other harm done by making R1 and R2 very large. Okay. So, that is for the input side. Now, what is the current flowing here? It is simply Gm times this voltage. I will assume that we have already satisfied this condition. So, this voltage here is approximately equal to Vs. Okay. So, this voltage here, this is Gm Vs, this current here, this is Gm Vs. What is the voltage across this? This current goes into the parallel combination of Rd and RL. So, the voltage in this polarity is given by minus Gm Rd parallel RL times Vs. Okay. So, you can see that originally I wanted a gain of minus GMRL Vs. Okay, that was my intention. Now, this RD has appeared in parallel with RL, and you know that the parallel combination is going to be smaller than RL. Okay. So, this gain is going to be smaller in magnitude compared to the original gain. So, this RD also ends up reducing the gain. This R1 parallel R2 also reduced gain because this ratio is smaller than 1, but we could make this much larger than RS and get around that problem. Here also, if we make RD very large, then RD parallel RL will be approximately equal to RL and we get the same gain as before. Okay. In other words, this current goes into parallel combination of two resistors. If RD is much larger than RL, almost all of this current will go into RL. That is the idea. Okay. This RD does not draw any current. But what does this do? If you make RD very large, let us go back to the full circuit. Here we are calculating the operating point. We know that the voltage across this, what is it? Let us assume that the transistor is in saturation. So, it is carrying a current 200 microamperes, in general some ID 0, and in the operating point condition that ID 0 will flow through RD. Okay. So, the voltage drop across this is ID 0 times RD, and the voltage drop across the transistor VDS, the operating point VDS equals VDD minus ID 0 times RD. Okay. Now, you can see what happens. If VDD is fixed, if the supply voltage is fixed, then if you go on increasing RD, this VDS will go on reducing, the operating point VDS will go on reducing. Okay. And we know that VDS has to be greater than VGS minus VT for the transistor to be in saturation. Okay. So, for a fixed VDD, increasing RD drives the transistor into triode region. Okay. Alternatively, if you want to maintain a fixed VDS, let us say we wanted VDS to be fixed, you decide that you want to have a certain VDS and you want it to be fixed, then increasing RD requires an increase in the supply voltage VDD. Okay, because VDD will have to be whatever VDS you choose plus ID 0 times RD. Okay. So, because of these reasons, the drain bias resistor RD cannot be increased indefinitely. Okay, because you do not have unlimited supply voltage, you have to live with some supply voltage that is given by the battery. So, you can't increase RD indefinitely, which means that you have to live with this reduction in gain. Okay. This part, the reduction in gain due to this is easy to solve, the reduction in gain due to this is not. Okay. So, these are practical things that come about. We have to set up the right operating point in the transistor. We do need R1 and R2 and also RD. Okay. And they do have some effect on the operation of the amplifier, that is that they end up reducing the gain. As far as the gate bias resistors are concerned, you can make them very large and reduce this effect, and as far as the drain bias resistor is concerned, we can't fix it very easily. Okay, because that requires an increase in the supply voltage. Okay, otherwise you will drive the transistor into triode region. So, that is not that easy. When we have this prototype common source amplifier, we have to live with this shortcoming, and this RD usually will end up being comparable to RL. So, you will have some reduction in gain. What this really means is, if you want a certain gain, you have to also take into account RD while designing it. Okay. So, that is a summary of the common source amplifier, including all the details. So, this should give you a pretty good idea of first of all, if you see a new circuit, how to start analyzing it, and also all the practical constraints that come about. Okay. Although our functionality is the small signal incremental functionality, and we wanted a gain of minus GMRL, because of the biasing components, we can have some reduction in gain or some effect in different circuits. Okay. All these have to be analyzed.